Okay guys, so in the last video you have seen that we had a simply supported beam which was subjected to your UDL, and we have drawn SFD and BMD. Okay, and as I promised, in this video I will discuss about how to draw bending moment and shear force diagram for a cantilever beam which is subjected to your UDL load like this. Okay, so first let me clear this canvas. Okay, so let's start. So very first we have a cantilever beam like this. Let's say this is the cantilever beam A and B. Okay, and it have a total length of, let's say, L. Okay, and now the loading is something like this. Let's say the beam is subjected to UDL load for a length of A from the free end. Okay, so this is the fixed end and this is the free end. Okay, so now let's mark this point as C. Okay, and we have to draw first SFD, shear force diagram, and BMD. Okay, so this is the third part of this series, how to draw SFD and BMD. Okay, so let's first consider a section. Okay, so now we are going to consider a section at a distance x. Okay, from this free end. From this free end, we have considered a section x. Okay, this is the section. Okay, so now what we have to do first, cut out this part. Okay, we have cut out this part, and it is subjected to UDL W. By the way, the intensity is W. Okay, small w. And here we have two things. First is your shear force. Okay, let's say this is Bx, and we have a bending moment. Okay, let's say this is Mx. This is our assumption that Mx is acting clockwise and shear force is acting upward. Okay, now the whole system is in equilibrium, so of course this part of this beam is also in equilibrium, no doubt. That means there is no resultant force acting towards vertical direction, so the summation of Fy is going to be 0, and this will give you that shear force, this is acting upward, this is our assumption, so positive, and minus the UDL, that is W times X acting downwards. Okay, that is why this is negative, and this is equals with 0, and this gives us Vx is equals with Wx. Okay, we have got it. And the next one is we have net resultant moment for this particular element of this beam is 0. Okay, so summation of moment about this point, let's say this is O, is 0, and we are considering clockwise moment as positive. Okay, and here you can see there is no component of moment due to this shear force because this is passing through this point, and also the UDL load, this red one. Okay, this red one is causing clockwise rotation about this point. Okay, and the net load is W times X, and it is acting at a distance of x by 2. This is the resultant. Okay, I think you are already familiar with this type of things. We have already covered in second part and first part. Okay, so here this is plus Wx time the distance. So the distance is, this one is x by 2. So Wx time x by 2 distance, this is 0, and it will give us Mx as minus Wx square by 2. Okay, that means our assumption here is wrong, and it is actually acting like this instead of this one. Okay, so let plot all these things, and first we will plot the beam. Let's say this was beam, this is the UDL load, this is point A, this is point B, this is point C. Okay, so first draw the SFD. So this is the x-axis, we are drawing now SFD. Okay, at B, x is how much? At B, x is simply, at B, x is 0, so shear force is also 0. It's okay. At C, x is how much? A. Here is the dimension, so shear force is going to be W times A. Okay, now positive or negative? Well, our assumption was correct here, because in equation it is positive. Now about this point, okay, about this point, this is creating a clockwise rotation. Okay, so now it is positive, so at C it is W times A and positive. Okay, now from this equation you can see that B or shear force is varying linearly with x. So from B to C it is varying simply linearly. Okay, so we have plotted the shear force diagram from B to C, simple. And now we will plot the bending moment diagram BMD similarly from B to C. Okay, so at B, x is equal to 0, so put the values in this equation, you are getting moment as 0, it's okay. And again at B is equal, at C, x is equal to how much? A, this one. Okay, so we are getting moment is equals with minus W square by A, sorry, 2 by 2. Okay, so our assumption was wrong, that's why in this equation we have got negative sign. So actually this is acting like this. Okay, so that means this element, if we draw this element, okay, under this moment is actually bending like this. Okay, so in the last two part of our discussion, every beam element was bending in a happy manner like this, so it was positive. But here it is like this, it is sad, so negative. Okay, so bending moment is negative, and we will plot towards downside, that is minus, and it is W a square by 2. Now how it varies from this point to this one, or from point B to point C? Okay, here you can see it is varying parabolically. Okay, so again same confusion. Before that, let me clean some portion. Okay, so previously you have seen that in case of the simply supported beam, we have drawn the bending moment like this was simply supported beam, and it was our UDL load. And if you can recall that our BMD was like this. Okay, so here the bending moment diagram is going to be like this. Correct? Not at all, not at all. Okay, that is why engineering cannot be memorized. Okay, so to draw this one, initially our choice was which one? Yes, who have already seen my video, they can understand. Initially we drawn like this, but that was nullified by the shear force diagram. The shear force diagram was like this, and this shear force diagram suggests that the bending moment diagram should be this one. Okay, not this one, not this one. So just like that, what was the equation, governing equation? Can you remember? Yes, dmdx is shear force. So the slope in the bending moment diagram should be equal with shear force. That means if shear force increase, the slope will also increase, the slope of the bending moment diagram. Okay, and in this case you can see, if we consider from this side, okay, here you can see that shear force is simply increasing, so the slope of the bending moment diagram should be increased. But here you can see, here this was the slope, but here the slope is 0, so the slope is decreasing, but it should be increasing. So the actual shape of the bending moment diagram is like this. The correct one is this one. Here the slope is 0, here this is maximum. Got it? How to draw it? So never try to memorize anything, okay? Because engineering cannot be memorized. Okay, so we have completed 50% to draw SFD and BMD, and here you can see that we have completed only from B to C. Okay, so what about from C to A? Here the loading pattern is completely different. Okay, here it was UDL, but here there is no load. So we will consider separate section for this particular portion, that means from point C to point A. Okay, so before that, let me clean this. Okay, so let now consider a section in this location here, and this is now our new X. Okay, and we are considering this section here. Okay, so separate this part, this one, and here the beam now looks like this. Okay, and the loading is acting only for this part, that is for length A. Okay, and the total length is X, total length is X, and we are assuming that the shear force is acting here upward, Dx, and also the bending moment is acting here anti-clockwise. Okay, anti-clockwise, that is mx. Okay, so from the equation of static equilibrium we can rewrite Vx as, I'm not writing elaborately because just we have discussed how to write down the equation. Vx is simply coming as W times A, no more forces. Okay, and it is not varying at all. Okay, because after this point the shear force is constant. The total WA load is acting on each and every section after this point. Agree? So Vx is simply coming as WA. This is the equation of the shear force diagram. Okay, or shear force at any section from this point to point A. Okay, and here we can also say that this resultant is actually acting at a distance of A by 2. Okay, the total length is A, so it is acting at a distance of A by 2 from this free end, Okay, so to find out the equation of the moment, now we can rewrite it as mx is equals with the force, that is W times A, okay, into the distance. And what is the distance? This is the distance here. Here you can see the distance is this one. And what is this? The total distance was from this end to this end, it was x. Now it is acting at a distance of a by 2, so x minus a by 2, this is the distance. Okay, so WA times it is coming as, well, let me use the red one, WA times the distance, and that is x minus a by 2. Got it? So now let's try to plot this one. So here you can see from this equation, well, shear force this color. So from this equation you can see that shear force is constant from point C to point A. Okay, and the value is simply W times A. Okay, and what is the sign? Well, here you can see that our assumption was correct. Okay, because in this equation there is positive sign, so Vx is creating a clockwise moment about this point, about any point, okay, within this element, so it is positive, so positive WA, and here you can see it has matched with the previous one, so there is a continuity. So this is the shear force diagram. Now let me complete the bending moment diagram also, and here you can see that bending moment is varying linearly. This is a function of x, not x square. Initially it was a function of x square or parabolic, so here it is linear. Okay, and at a distance of your C, let's consider C. Okay, and at C x was simply a. Okay, so at C x was a, so moment was minus W a square by 2. Okay, so value is matching. Okay, and here you can see that our assumption actually, sorry, this is plus, so here our assumption is actually matching. That means the element is bending like this, so shared one, so negative. Okay, so both the values and sign is matching, so there is also continuity in this case also in BMD. Okay, now from point C to point A, how it varying? It is varying linearly. So at point A, x is how much? Simply L. Okay, so moment is coming as WA times L minus A by 2. Okay, so here this is this one. Okay, and from this point to C, it is varying linearly. It is not parabolic. Don't confuse with this one. Well, let me use some different color. Okay, so here this is linear. Red one is linear. Okay, but green one is parabolic. This is the complete shade of SFD as well as BMD. Okay, so that's it.